We didn't go very far in the nutrition labeling lecture last time, so I stopped earlier than when I usually stop, so my recap questions, we haven't gotten through this yet. But is nutrition labeling required for all food? Do you remember? No. What examples of food we said we don't require? Grace. Bignon. Bignon. Benoit. Yeah. Sometimes I get it right. Individual packaging, Ali. Produce, Axel. Alcohol. Supplements. All said. All said and done. Okay, good. What agencies regulate nutrition labeling? What? Nathan, yes, you're Nathan. FDA is one. Not Sam. This is Sam. You don't tell me. You're Nick. Okay. FSIS, which stands for Food Safety and Inspection Services. So, Food Safety and Inspection Services actually regulate the eggs and meat in Turkey, I believe, while FDA regulates everything else. Okay. Without looking at your notes and from what you know probably and heard of, can you answer this? What are new changes in nutrition labeling? Okay, Sam.
One of them is going to be going to require labeling
Added sugars, perfect. Alex?
The calories is bigger.
Calories are bigger. Watch what you eat. Go ahead, say your name. Not Riley. Riley, yeah, Riley. You don't have to say the calories from fat. Zach?
Certain vitamins were taken away, like C, vitamin C was taken away, and D was added.
Exactly. Vitamin A and C, both were taken away. Jacob? Exactly, they added that. That's very good. There's one more mineral. Ali? Yeah. Exactly. And then? Potassium. Okay. Good. There you go. Covered. I think I did mention this briefly. What type of analytical methods are required to obtain nutrition label? When I say what type, and sometimes in an exam I ask this question, what type, people get confused. It's like, what do I mean by what type? Okay, I'm going to tell you what I mean, so you remember it if you see it in an exam or a quiz. Is it official methods of analysis, primary methods of analysis, or secondary methods of analysis? What do you think for nutrition label you need? Do you remember the difference, Grace, between primary? Mm-hmm. Okay, yes, very good. Primary are those official methods that have been validated to be accurate and precise in different labs, and they are published in by official sources like AOAC, AOCS, AACCI, and etc. And then the secondary are quick methods usually calibrated by primary methods. So nutritional labeling requires official methods of analysis. And we'll go over this. When can you claim calorie-free? Do you know offhand when can you claim a product is calorie-free? 10. Less than 5 calories. 0 to 5 calories or less than 5 can be claimed as calorie-free. And we'll talk about compliance later. So don't worry about that. So here is the new label, which you've already said almost everything there. The serving size changed, calories is bolded and bigger. You no longer have calories from fat. Let's see, added sugars there. and then removed vitamin A and C and added vitamin D instead. Um, can you guess why that is? First of all, why did they have vitamin A and C originally on the label? Okay, Sam?
Because those were at one point nutrients of concern, but now they're so heavily supplemented in other products that we don't have issue.
Perfect. A and C originally we had concerns with deficiencies. As of now, we don't. Vitamin C is supplemented. Vitamin A is supplemented. Vitamin D, we do have quite a bit of deficiencies due to exposure to sun and reduced exposure to sun. So vitamin D now is a concern. Potassium was added due to health benefits of potassium regarding blood pressure, muscle health. Yeah. So it's good to have that. So these were the reasons to make these changes. And we talked about when it was proposed, approved, and compliance date. So as of now, it's not yet required to be this kind of label, but some are already moving towards this label, but really they won't be needed to comply until 2020 or 2021, depending on the size of the company. So these are the different components that you would see on the label, the macro, I mean, not kind of the non-vitamins and minerals ones, and they have the daily recommended value. So this is the daily recommended value for each of one of those, which you really need to know by heart. No, just kidding. So you don't need to know by heart. It's good reference for you. The source is, of course, the CFR source is numbers where you can find them, code for federal regulations. And for nutrients of vitamins and minerals, you have what is called recommended daily intake. And also these are the different recommended daily intake. So for example, when you do the AA, atomic absorption lab, you will be looking at calcium and iron daily required daily intake to calculate the percent required daily intake from your food product. Each group will have a food product to determine calcium and iron in. So you'll be using these values there. This is a rounding table for how you would report it. So of course there's no decimal points, and so how would you report the different nutrients based on the amounts? This would have been really helpful for your projects if you were going to do projects, so a lot of this information would be useful. But you might need this when you are developing nutrition label for your capstone. So when you calculate or determine different components in your capstone product and you want to generate a nutrition label, this would be important information. So reference, so FYI. How do you round and report? Okay, so looking at calorie, how do we determine calorie for the label? There are different ways of doing that. One easy way, usually you calculate the calories per the different components. So you have protein, carbohydrate, and fat. These are your sources of calories, non-alcohol foods. So do you know the calories is actually kilocalories, but with the capital C refers to kilocalorie. Do you know how many calories per gram of protein there are? Nathan? 4. And carbohydrate? 4 as well. And fat? 9. What about alcohol? 7. Oh, gosh, good. All right, so you would do that. You would calculate. And you can calculate based either with or without the dietary fiber. So if dietary fiber is a big component of your nutrients, so you better subtract that because dietary fiber does not carry calories. It's not digested, it's not absorbed. So one thing is important is how do you determine percent daily value of protein specifically? Because protein have differences in digestibility, how they get digested in our body. So not every protein we consume is digested 100%. So if you have 10 grams of protein and you have 80% digestibility, then only 8 grams of protein is available for your body. So in order to determine how much of that 15 or 10 grams of protein actually meet daily value, you have to take into account the quality of the protein. And we're going to talk about the quality of the protein in chapter 24 in more detail and go over those two different methods. So you will probably hear about protein efficiency ratio, PER, and these are for infants or children under 1 year of age. The reason we use PER for infants and young children is because the assay used is they use infant baby rats. So it's based on the growth ratio of the baby rats when they consume protein. And we'll talk about that later in more detail. This assay, protein digestibility corrected amino acid score, we'll talk about it in more detail, but it takes into account the limiting amino acid, the amount of limiting amino acid, as well as the digestibility of the protein. And the assay is done in adult rats, so it is for foods for children 1 year and older and adults. So both are ratios, so the greatest number is 1. So when you have a PDCAS of 1, then that means all of the protein in your serving is available for you. So you multiply by 1 and all the protein is there. If the PDCAS value, let's say, is 0.8, then the 10 grams of protein you multiply by 0.8, you only have 8 grams of protein that you can claim out of the daily value. So these are important to note, different from fat and carbohydrate, obviously. So which of these are correct? Percent daily value for protein is found on the label of which of these? Anybody? Yes, Riley? B and C? Anybody else? Go ahead. B and D. So you didn't like C, you didn't like D. Okay. Any other opinions in the room? Yes, Jordan? No, not Jordan, you're Devin, sorry. Yeah. What did you say? B? B, C, and D. So yes, all of this. So we have nothing to do with reduced calorie. And definitely if you're making a protein claim, if it is for athletes that are looking to build their muscles, yes, that would be there. And then for food products for children under the age of 4, yes, so that's when you see percent daily value for protein. So compliance. So there are government regulations and producers of food need to comply with these regulations. So when it comes to nutrition labeling, there is a compliance on how you collect the samples and how many replications in order for you to come up with the numbers that you put on your nutrition label. So the compliance includes sample collection and replication. We're going to talk about that in chapter 5 when we talk about sampling and sample preparation. Methods of analysis. So for FDA, they have certain methods, mostly AOAC methods, unless they specify a different method in the Code of Federal Regulation. The FSIS, they have the USDA Analytical Chemistry Laboratory Guidebook, or AOAC methods if the guidebook does not have that particular method. So they have to comply with the methods listed by these two agencies. Now, level of compliance, in this case, you really need to know this information. Level of compliance. So let's say they have added a nutrient. So it's fortified with a nutrient in processed food. They should have 100% or greater than what they claim. So if they had 90% of what they claim, they are not in compliance. So that's why when let's say they fortify with vitamin C and an orange juice and they process, they always have to calculate that after processing they're going to lose some vitamin C, and during storage vitamin C is going to degrade as well. So they put in much more than 100% of what they claim, because at any point in time when they measure during shelf life, they cannot fall under 100%. So they make sure that they put in there more than what they claim to account for shelf life. Naturally occurring, that means endogenous, already there, it's okay to be 80% or greater. So it doesn't have, they don't have the 100%. They don't have to meet the 100%. However, for components that we care about, like calories, sugar, total fat, saturated fat, cholesterol, sodium, all of these have adverse effect if consumed in higher amount. In this case, the values should not exceed 120% of what they claim. It has to be less. 80% is acceptable for these components. But it can't be 130% of the total fat that they claim, for example. So these values are important for you to remember. Nutrient content claim. So they are defined by both agencies, FDA and FSIS. So they are based on the level of a nutrient, obviously. So you have different terms that can be used: free, low, lean, light, reduced, less, good source, more of, high, healthy. So all of these, there are contents associated with them for you to claim high or low or good source of or light or free. So the previous edition of the book used to have a table labeled 3.7. It's no longer in this current version, but it actually gives you an idea of, for calories, for example, what can you claim as free, low, and reduced, etc. It's a long table. I have it here for reference only, for your reference, to see what you can claim for different amounts. Of course, you can find this information in the Code of Federal Regulation for every nutrient. So it's just there for your information. Health claims, there are several. You can find them in table 3.6 of the book, chapter 3 in the book. Calcium and osteoporosis is an example, dietary fiber and cancer, dietary fat and cancer, sorry, sodium and hypertension, fruits and vegetables, folate and neural tube defects, sugar, alcohol, and dental caries. These are, shouldn't that be dietary fiber? Why dietary fat? There's no dietary fat. I don't know what I have there, but I think it's dietary fiber and cancer. Please correct that. Huh. This is the first time I've noticed. Okay. Dietary fiber, right? Yeah, okay. I don't know what I was thinking. Okay. So that's the end of nutrition label. Again, there's a bunch of them. This is just an example of what's out there. Already went through what's going to happen in the lab. Some of you already did the lab, so let's just move on. Any questions at all related to lecture, related to lab? Anything? You can interrupt me at any time. Okay. Huh? There is a question. Caitlin.
Week 2 isn't showing on
What is not showing?
the week 2.
I did not open it, possibly. I added stuff and I probably did not. It's technically not a participation point, but it's okay. Okay, see, we have wonderful TAs that really likes to give you points. Okay, oh, I did not open it. I did not open it. Okay. So, yeah. Okay, I'll make sure. Cancel. Anyway, you should be able to see it now, unless I need to log in again. I'll double check.
No, I have access to that one now. So we get the next two problems.
Okay, perfect. Thank you. All right. So this is chapter 4, and we'll be dealing with data analysis the entire semester, basically, with data in the lab. So this is kind of really an overview. And many of you might remember this from very simple math in high school or even middle school. But it's a refresher because you're going to use it quite a bit. So we talked about precision and accuracy a little bit last time, but if we have a method A is more precise in measuring glucose content than method B if what of the following? Claire. D, A, and C. Okay. Any other, anybody agreeing with Claire, Ali? Just A. So we're going to go with Ali. Okay, so it is A because a standard deviation is really a method, a measurement of precision. So when we say precise, that means how close your replications are to each other. So standard deviation takes that calculation into account for replication, and this will give you the precision of the method. So the lower the standard deviation, the more precise is your method. This has to do with percent relative error and accuracy. We'll talk about that later. So like I said last time, any analysis that you do in a lab, you have to replicate because there's always source of error. No matter what, the source of error can come from you as an experimenter, or it can come from the balance that you're using or the pipette that you're using. So there's always what we call experimental error. So we cannot trust one value by running one replication. So there's always you're running multiple replication. The more steps you have in your method, the more replication you should be doing. So usually they say, okay, you can do duplicates and then that means 2 replication and do statistical analysis. That's the weakest statistical analysis that can be possibly done with 2 replication. So 3 replications, sometimes you need 6 replications. It depends again on the method. So when you have replications, then you can determine the accuracy and precision and you evaluate that of your method. So first thing you would do is you measure the central tendency. So you would get mean and median, which you already know what they are. Of course, you know the difference. What is the median? Okay, Kim? Yeah.
You'll have a set of data
Yeah.
essentially.
Yeah.
And the middle will be where the majority of all the points are on the graph.
Yes, so the median is actually the midpoint of your data. So that is your median. Sometimes if you have even number of replication, then your median would be the average of the 2 in the middle. So that's what it is. So we always, in the lab, we're not going to necessarily look at median because we'll be doing duplicates, triplicates, or replicates of 4. So mainly we'll be determining the mean or the average of your data. And then we're going to look at the reliability of your analysis by determining accuracy and precision. We'll talk about how we determine these two and how the error really influence both. So there are errors that you would do will influence your precision, and then other errors will influence how accurate your data is. So we'll talk about the different errors. Specificity, we talked about that briefly last time. Specificity is how specific is your method. We gave an example. Are we determining total carbohydrate, or we want to determine total glucose specifically, not sucrose, for example. Sensitivity and detection limit, and often people confuse these two and think they mean the same thing, but they really don't. Do you know the difference when we say how sensitive the method is versus detection limit or detection threshold? Detection limit and detection threshold means the same thing. If you hear threshold, that means the same thing as detection limit. Do you know the difference? Or can you guess the difference? All right, I'll go with, go ahead, Kim.
I'd say detection limits, like what's within your linearity on a curve.
You are close there. I will correct that in a minute. Go ahead and tell me what you want to say, Fan.
For example, an instrument can test the lowest amount of the materials. Is it detect-
Concentration, yeah. What is the lowest concentration that a method or an instrument can detect with certain accuracy? Yes, but what you were saying is also true in a sense that when we're doing a calibration curve, we have to stay within the linear range of to determine an unknown, which is very, very true. Now, sensitivity means something a little bit different. Is how low of a difference can an instrument or a method detect? So if you have a sample that is, let's say, 1% glucose, and another sample is 1.05% glucose, can your method detect a 0.05% difference? So that means how sensitive your method in determining the smallest difference between your samples. Curve fitting, we're going to do that a lot, especially when we are determining unknowns in a sample, like when we're doing the caffeine lab, determining caffeine in different beverages. So you're going to have a standard curve. And a standard curve, you're basically fitting your data in a line, and oftentimes it's a linear regression line. And you're getting equation of the line, and you're getting an R squared. Well, the correlation coefficient is R, is basically how well the data fits a straight line, how well the data is linear. And coefficient of determination is really your R squared. That means how much you can trust the accuracy of your equation in determining your unknown. So the closer to 1, the highest is the prediction power. Okay, we'll talk about each one of these individually, so we'll come back to those. And reporting results, very important thing that we'll go over and very confusing is significant figures. So there are rules about reporting your data within a certain number of significant figures. We'll go over that, but sometimes it gets too complicated. We'll try to simplify it as we go for each lab. But it's very important that when you report your data, you don't put 10 decimal points in your average. So you have to report your data within the significant figures that make sense based on the experiment and the analytical methods that you've used. And then rejecting data, it's a tool that we sometimes use. If you have 4 replication, 3 are very close and 1 is really far away, and it's tipping off or screwing up your mean, basically. You're getting a mean that has really bad percent relative error or accuracy, very far from the correct value or the standard value. So in this case, there is an equation that you would do and carry out to determine if you can throw out a data point. And oftentimes we do throw out a data point, and then your average makes more sense, your precision is enhanced, and your accuracy is enhanced. So that's why replication is important, so that you can throw out a bad data point. Okay, so what I'd like you to do is pull out a piece of paper, and this is the first +2 opportunity for extra credit. We're going to do some solving of some calculations. We'll start simple. Write your name. Okay. So let's start with very simple calculation. You have 5 replications for determining of moisture content. Just determine the mean and the median. Let's just start there. When you have a value, you can raise your hand, can take that value from you. Okay, Riley? Yeah, go ahead. Tell me your mean. Yep. Yes. Okay, so it's very simple calculation. Getting the average and finding the median, which is the midpoint of your data range. Okay. So we talked about precision and accuracy last time, what we mean by precise and what we mean by accurate. So what is A? Is it when you collect data and they're all here, do we call this good precision, good accuracy? What do we call this? Nico?
That's good precision but bad accuracy.
That's good precision but bad accuracy. This could be due to a simple thing that your pipette that you're using is not calibrated. So you're getting a systematic error. You're always making the same error. Instead of pipetting 1 ml, you're pipetting 0.8 ml without knowing because your pipette is not calibrated. So everything else is good. You're getting similar results, but they're way off. Okay, what about B? Nathan? Yeah, you're right there. Good precision, good accuracy. What about C? Both. This is terrible. Whatever you're doing is really bad. So you're not getting good precision and you're not getting good accuracy. And this is very typical of somebody starting an experiment that has many steps and the first time they're running it. That's how the results will look like. So I think Nico was Nathan. Yeah. You guys need to start learning their names, like I'm learning their names. A couple of years ago, I had a TA and we had a bet who was going to learn the student's names first. And for the first time in 11 years, a student, TA, learned the names before I did. And that was Amy, of course. Amy's weird. Okay. So I should say we should have this competition so you guys can learn their names. All right. And the last one, D? Go ahead, Fan. Yes, good accuracy and bad precision. And this could be that you're having just some experimental error while you're running your experiment. But with more practice, you'll get good precision and accuracy. All right. So accuracy is determined by relative error. So it's a term that we calculate if we know the true value. Usually the true value is like either a reference that is published, like we get from the USDA. You're going to do that a lot. The USDA website is going to provide you percent protein in your baby cereal that you're measuring composition in the lab. So you will get percent protein in the lab and you have your USDA reference. The USDA reference will be your true value for that particular product. So when you have access to a true value, then you can determine percent relative error. You start with calculating the absolute error, which is your average, the difference between your average and the true value. So you can have the absolute as you don't have to have a sign. If you have a sign, negative or positive, you just know that your average is lower or higher than the true value. But really, when we say absolute, it doesn't really need to carry a sign. And then you have your relative error, which is the difference by the true value, and percent error, which is the difference by the true value times 100. So usually if you have less than 5% relative error, that means your accuracy is excellent, it's pretty good. Rule of thumb, if you have 5 to 10%, that means it's okay, it's acceptable, it's not really bad. But anything above 10% relative error, that's where your accuracy starts to consider not so great. Yep. So let's continue with calculation on that same sheet of paper with 3 replication from a mechanical pipette, which you'll be using a lot in the lab. When you're ready, you can raise your hand with an answer. Anybody with the mean already? Okay, Evan?
0.9961.
Yes, all right. And what's your true value in this case? 1. Thank you, Zach. Anybody with absolute error? Okay, go ahead. Right. Yeah, it's okay to be negative. Yep, okay. And the relative error? What? 0.00? Yeah, so it's the same. So your absolute error is the same as your relative error because your true value is 1. So what's your percent relative error then? Go ahead, Grace. Yes, 0.39% negative. You can, like I said, you can add that negative to show the direction, or you can leave it as absolute value. So here it is. Okay, ready to move on? Okay. So let's talk about precision a little bit. So standard deviation is the first measurement you would measure or determine